This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Hello everyone, this is Felienne for Software Engineering Radio. Today on the show I have Claire Le Goues. Clara is an associate professor at Carnegie Mellon, where she works on applied program analysis and program repair. She holds a bachelor's degree from Harvard and a PhD from the University of Virginia. Before grad school, she spent some time in industry at IBM, where she specialized in XML processing. Claire, welcome to the show.
Hi, Felienne. Thanks so much for having me.
So today we're going to talk about automatic program repair, which is a pretty interesting topic, but something not everyone might be familiar with. So Claire, can you take us through the basics? What is program repair?
So that's a great question, Felienne, at a high level. The idea is that you're a developer and you're working on code and you have a bug. And there are many different ways we might say that we have a bug. For example, and I think a very common circumstance is that you have a regression test that fails, or maybe you write a new test and it also fails. It doesn't give you the answer you expect. Research in automatic program repair tries to come up with ways to automatically take, for example, that failing test or a failing linter check or something like that and produce a patch for you that automatically fixes it. And so then you don't have to.
So to me, that sounds like debugging. There is a mistake and I just need to fix the mistake. We just had a show on debugging, actually, show 367, if people want to listen. What is the difference between debugging and program repair?
So in debugging, there's a lot of really interesting work in debugging. I need to listen to your show. And the idea there is to really help the developer a little bit more interactively. So debugging techniques are going to point out to the developer where the problem might be to help her manually construct her own patch. Whereas the idea in automated program repair is to really remove that last step. So the developer doesn't have to spend time tracking down or trying to understand or putting the pieces together. Instead, you can imagine it's almost the creation of an automated pull request. You have a bug and then you come back in some amount of time and the pull request has been created to fix that bug for you and you don't have to. And the techniques can be related because sometimes you can look at a patch for a bug and it helps you understand it. And in there are a few deployments of program repair and that's really how it's used. The developers are still reviewing the patches before they're deployed. And so I think there's definitely a relationship here between patch generation and debugging. But the idea really is to automate a lot of that hard work that the developer needs to do, even with hints, to track down and change the code to fix the bug.
So you mentioned a few interesting things, and I want to zoom in on one. You said generate patches, and that's plural. So does that mean that if you run automated program repair, that multiple suggestions are being done and that as a developer, you get to pick from a bunch of options to decide which one is the most preferable?
So that actually really depends on the technique that we're using. There are some people who produce some of the techniques produced by researchers will do that. Some of my work actually is capable of producing multiple patches for the same bug. And then there are other techniques that work to just simply construct one patch and present that to the developer. So it depends a little bit on context. And I think context really matters for this use case because although, in the current deployments we're seeing in industry, the use case I described to you is, I think, the most common, where we have a bug or a problem or a regression test failure and a patch is presented to the developer to consider. You can also imagine this kind of technique being used overnight when your sysadmin's asleep, responding to some kind of automatically detected vulnerability or intrusion that's detected. And then this kind of technique can automatically fix the problem, at least until someone in the morning can come in, think about maybe the better way to reconfigure the system to avoid it. So in that case, we really only need one patch because you need to stem the bleeding in your system. So I think there are a bunch of different options for where this technology might be useful, depending on kind of the type of system you're running and your development and deployment context.
So here also you mentioned something interesting in the use case you were just describing where something is running overnight, because there also finding the bug is being done automatically, right? So the system detects that there is a bug and automatically comes up with a patch and automatically deploys it until someone is able to address the problem. Is that what you were describing?
Yes, that is what I was describing. And so while I would say the bug detection is kind of a separate problem, there's a lot of research in that. It's very complementary to the kind of work that I'm talking about that we do in automatic program repair. And in fact, some work at Facebook that they've been discussing recently does connect research in generating tests to find bugs to work in generating bug fixes to fix those bugs. So even though they're two separate problems, they're very complementary, and we're seeing them being used together to try and make software better in practice.
But typically, to summarize, you would say that finding the bug is not part of automatic program repair. The part that is automatic program repair is generating solutions. And then the developer in let's say the third step, still has to verify if these patches are actually what they want.
I mean, yes, I think that's a good summary. I suppose the developer doesn't have to, but in practice, that's kind of the assumed model right now, that the developer would then review it in the same way you'd review a bug fix from a teammate or from, something submitted to a bug bounty program. People still review patches practically these days.
And then the patches that are generated are already tested to a certain extent because only valid patches are being generated, right? Only patches will be generated that at least make all the existing test cases pass. It will never generate patches where half of the test cases are broken because then it's not a good patch.
Yes, exactly.
So indeed, checking the patch is more like you would do code review. Does this make sense? Is this logical? Can other people read this? It's more that type of verification than actual testing because that should already be taken care of by construction.
Yes, and by construction, the tests will pass because that's one of the kind of key goals of these techniques. But yes, it turns out there are usually more than one way. Almost always there's more than one way that you can fix a bug or make tests pass. And so what we see is sometimes humans will say, oh, yeah, that's fine, but actually I would want to fix it in a different way. And that might be because there's a different way that's more readable, that better fits their mental abstraction of the system. There's any number of reasons you might prefer one patch over another. But there are certain quality checks that any program repair technique is already doing to make sure that it's not doing something completely disastrous.
So it sounds pretty magical, right? Oh, I have a bug, and instead of programming myself, I can just have a machine do it for me. Can you help us understand what type of bugs could be fixed in theory with automatic program repair?
So that's a good question, Felienne, because I think as your question implies, automatic program repair techniques certainly can't and don't claim to fix any kind of bug or any kind of test failure you're going to run into in practice. And coming up with a very precise answer to this question is difficult. I think we've struggled with it sort of as a research community, but I can say that there are some kinds of bugs that these techniques are better at fixing than others. So, for example, most program repair techniques are only going to make very short patches, so only changing a few lines of code at most. That actually helps you fix a fairly large proportion of bugs in practice. Even when humans fix bugs, a large proportion of them don't require changing, multiple hundreds of lines of code, but it is limiting. Usually the kind of bugs that these techniques can fix are fairly local in their effects, so they only require changes to a few lines of code. These techniques are particularly good at fixing problems with control flow. So either bugs in the condition statement of an if statement, or even we've seen a bunch of these. Sometimes you'll have series of if statements, and they should be else ifs. So inserting an else where it was once just an if, that kind of control flow bug is a pretty good target. So you won't know ahead of time. And that's the real kind of the tricky part right now is, if you, the developer, knew that what you needed to do was move this block into an else block, then you wouldn't need us, right? So I think kind of the imagined use case right now is that the program repair technique will try, and if it succeeds, all the better. And if it doesn't, we kind of assume that a human will have to reason about the problem and think about it a little bit more deeply than current reasoning techniques can do automatically.
Yeah, so we cannot expect automatic program repair to, for example, come up with a new data structure to fix a certain edge case that affects 10 different classes in 3 different files. That type of repair, because of the scope and because of the number of changes, is probably unlikely, but something like changing a little bit of control flow is something that an algorithm can come up with.
That's an awesome summary.
Thanks. So now on to how do we do this? You already mentioned some things that such an algorithm can do. For example, move a certain block. How does this work? How does the algorithm come up with suggestions for the patches? What's under the hood?
So there are several different techniques that have been proposed, not just by my group, but by others as well. So I can kind of give you some hints about how some of them work. And I can start by focusing on some work that I know particularly well, because it's the work that I've been doing with my group really back since my PhD. And that is to, in our case, we use something called genetic programming to automatically evolve bug fixes for a particular program with a bug in it. And so what genetic programming is it's a technique that's inspired by biological evolution that can evolve solutions to problems. So in the case of a bug fix, what we'll have is a set of test cases, and we'll use those to evaluate the fitness of a potential patch to the program. So the fitness is just like biological fitness. It's your fitness for reproduction. You know, the birds with the stronger wings and the pointier beak that are more attractive to mates are more likely to pass on their genetic material. So in the case of a patch that we're trying to evolve, the number of tests it leads the program to pass, that is its fitness. Those patches are better and more likely to continue to evolve towards a solution. So what we do is we'll take a program, we'll do a little bit of analysis, some debugging analysis, actually probably using techniques you discussed in your last podcast, to try and figure out where the bug is more likely to be, and then generate a whole bunch of random patches, evaluate each of them for their suitability for fitness. And then if none of them actually solve the problem, lead all of the tests to pass, we will combine and mutate and select and cause those patches to reproduce to create a new population of patches based on the old ones, and continue until we hopefully find a patch that solves the problem.
So just to summarize, what you do is you have a certain edit, move a certain else block in, and that does really well. That change doesn't solve all the test cases, but let's say it fixes half of the failing test cases. And you have another mutation that is, I don't know, change the variable A to the variable B. It also does pretty well. And then they will have patched babies that have both of their characteristics, potentially, because there's some chance involved. And then if that does well, then that goes on to create a new population, and you repeat that process until all the test cases pass.
That's a really great summary. Exactly.
Now, then I'm still wondering how you come up with the first generation. How do you kickstart this project? I understand how it works once the ball is rolling, but what are some of the suggestions that start in the first population?
So that's also a great question. So what we start with is I sort of hinted at this, but it probably got lost in the later story about evolution. We're not actually going to just randomly change the program in any way. We're not going to change an open bracket to a percent sign, right? Because you can make a lot of changes to program text, and most of them are going to be extremely bad from the purposes of being likely to fix the bug. So the first thing we're going to do is start with the tests and do some debugging analysis to narrow down the slice of the program where the bug is more likely to appear. And we could do this automatically. It's almost like doing printf debugging, but it's automatic and it has slightly better math to figure out the probability that a location is likely to be the source of a bug. So that's the start, and that the edits are only going to be concentrated there. And then we really just randomly generate edits. We randomly generate these patches by composing one or more of a subset of edits that you might do to a program. There's been a lot of work on what those edits should be. We originally started really by just moving blocks around. So inserting one statement in C after another, replacing a statement with another statement, or just deleting things. Since that initial work, there's been a lot of exploration of maybe more natural things that you might be more likely to do, like insert a null check, for example, or replace one method call with another method call that uses the same arguments. These kinds of templated things that we see that humans do if we look at kind of the history of a bunch of open source projects, for example. So this isn't editing the program to randomly change your open bracket to a percent sign. It's really at a kind of a higher level of code abstraction. So these changes will almost always result in code that compiles, for example. But it's really at the point that you set the sort of templated edits you might try. At that point, generating that first population is random, guided by some probabilities and some analysis that we do on the initial program.
So to summarize that process, you have something like a database of edits that developers often make, like moving blocks, inserting null checks, that exists. You know what developers more or less do. And these are things that you use as a first population. So they would mainly be things that compile, because as you said, it does not make sense to change a closing bracket to a percent symbol, because that will never compile. The edits are always bigger units that developers might realistically also apply.
Yes, exactly. The edits are take into consideration the structure of code and are really kind of inspired by the things we might actually expect a person to want to do to that code.
Okay, that totally makes sense. Then I want to come back a little bit to that debugging analysis that you mentioned, because you said somehow we know what parts of the code are more likely to contain the issues than other parts. Can you explain more about how does the code know, how does your algorithm know what parts of the code are more buggy, more likely to be the source of this mistake?
So in this work, we're really relying on insights from researchers who do automated debugging research. But the idea, I think, is pretty intuitive to people who've been programming. If you have a failing test case and you have some passing test cases, one way you can try and understand what's happening is just by running them and seeing which code elements are executed. On the failing test case, maybe lines 1 to 5 and line 8 are executed, and then you have a seg fault. Whereas on the passing test cases, maybe lines 1 through 5 are executed, and then lines 10 through 15. And so lines 10 through 15 probably don't contain the bug. They're not even executed on the failing test case. So we're not going to try and make any changes there. We're going to set the probability that they are modified by the random process to 0. Whereas lines 1 through 5, which are executed by both the passing and the failing test case, those might be initialization code, for example. They will have a different probability. They'll have a probability greater than 0. And that line 8 that's only executed by the failing test case, that'll also have a different probability. There's a bunch of research in what those probabilities should be. But if you think about it that way, it's really just seeing what is executed by which test cases and using that information to figure out where you should start to make changes. And it's very similar to something you might do with a debugger, stepping through an executing test case to see what's executed and even what the values of the variables are. And also fairly commonly used with logging or printf debugging if you're doing something like that. Just say what's being executed when on which test cases, and that'll influence which lines you're likely to try and change first.
Yeah, I very much like how both this automatic debugging you're describing and also the automatic program repair are very much based upon what human developers do, but then just machines can do it quicker and more efficiently and can combine different things together. But at its core, the processes are still very similar to what a human developer would do.
Yeah, I think that's accurate. I mean, we take a lot of inspiration for what might make sense to do to a program from what human developers do, because they really are kind of our gold standard right now. I do think, machines, when they make suggestions, when they evolve solutions, especially using something like genetic programming, they'll often end up doing things that humans might not expect. And that can be informative in its own way, I think, which is interesting. But yeah, I mean, the core idea, the hope is, these systems need to interact with human developers still, and hopefully for a long time, humans are going to continue programming. And so the idea is to really be inspired by what they do so that these systems can interact with the systems that humans are interacting with in kind of a symbiotic and cooperative way.
Got it. So I watched a really nice talk from you earlier as preparation for this show, and we will totally link that in the show notes. And in that talk, you were talking about two big different approaches that exist currently, the semantic and the heuristic approaches. Could you take our audience through those two approaches and what the difference and similarities between them are?
Absolutely. So the heuristic approaches, starting with the second thing you asked me about, that includes techniques like the one based on genetic programming that I described to you a few minutes ago. And it's heuristic because it's not using any kind of formal reasoning in any meaningful way. It's not using math. It's not using symbolic execution. It's not using symbolic analysis. What we're doing is we're executing the program, we're seeing what's run on it, and we're making these random changes in some principled way to try and influence the behavior in the desired way. And there's many other techniques besides the one I described that have this flavor. Maybe it doesn't use genetic programming, maybe it uses a different kind of random search, maybe it doesn't use random search at all, but it's really using a heuristic expansion of templates, for example, to try and fix the bug. So that's one category of techniques. they tend to work for a long time. Actually, they worked on larger programs than the alternative did. That's less true now. But when they were first proposed, those techniques scaled better. And they produce different kinds of patches as compared to the semantic techniques, which I'll describe next. The semantic techniques are using more of that formal analysis that heuristic techniques don't use. So the idea here is you're going to execute the test cases. And then if you think, because of the automated debugging that we were talking about before, that the bug is likely to be on line 5, semantic techniques will construct basically a formal or a logical specification of what the technique thinks line 5 should be, and then make use of program synthesis to construct code that does what it thinks the correct thing is. So the idea here is that we're still using test cases to narrow down the possible source of the bug. But instead of then honestly just making random changes inspired by what humans do and hoping it works, semantic techniques try and do some more formal analysis and then make use of more formal synthesis techniques to hopefully make code that maybe is more likely to even be correct by construction in some way. So if you have a test case that's failing because on input to a function, x is 2, and on return it should be 4. Let's say instead it's 6, right? The test is failing because x has the wrong value. These kinds of techniques will look at that function and say, well, something's happening to x on line 5. And I know on line 5 it starts off as 2, and I figured out that after line 5 it needs to be 4. What kind of code can we put there that would make x 4 after line 5? It doesn't even matter what's happening on line 5 if you think about it, because it's really just going to be replaced. And so what these techniques will then do is ask a formal program synthesis method. There's a whole bunch of techniques that can do this and say, hey, if I have a variable that starts off as 2, what is code that could make it 4?
A heuristic approach would say, oh, maybe it's 12, maybe it's 10. Oh, I'm going the right way. Maybe it's 4. Whereas a semantic approach would calculate the difference between 4 and 2 is 2. So clearly what I need to do is add 2. That's the difference between those two approaches, right?
Yeah, I think that's a good high level intuition. So a heuristic approach, and actually many heuristic approaches will say, well, I'm just going to grab code randomly from somewhere else in the program. Hopefully one of them will set x to 4. And oftentimes this actually does happen because code is fairly patterned even within the same program. A synthesis approach will ask a synthesizer, give me code that makes x 4, and the synthesizer will give it back an answer. Maybe it'll give code that says x equals 4. Maybe it'll give code that says x equals x times 2. It depends a little bit on some of the other constraints it includes. But that's how the synthesizer is going to be used to replace the code on that line to make x be what it needs to be.
Yeah, that makes total sense. Thank you for adding those examples. It's always a very good strategy for us to understand what's going on. I want to come back to one other thing you said, where you said a heuristic approach takes edits from other sources in the program. So that we talked about that database of this initial generation for genetic programming initially. And there I thought of it more as a database of edits that exists across all programs. But now I understand what you mean more is local edits. So for a given code base, you would look for edits that often happen within this code base. And that would be edits that you try. And you wouldn't have access to a generic edit database that would work on any type of code base. Do I understand that correctly?
So it's an interesting kind of point that you're making. I think that highlights sort of a key thing about these heuristic techniques. And I am summarizing a bunch of different techniques when I do this, just to be clear. The edits themselves can be provided from basically anywhere. They can be a database taken from across a whole bunch of programs. It could be from the local program, but that's actually less common. But the thing about an edit is that it doesn't necessarily contain all of the code, right? An edit is a change. So if an edit is, I'm going to insert something on line 5, I think of the insert as the change. But what's inserted? Like what code should be put after line 5? Or if I want to insert a null check, what should I be null checking? Right? Like what am I wrapping in a null check? What object am I checking for null when I do that? The change, the insert a null check, is provided in a database ahead of time, taken from a bunch of places. But the thing I actually end up checking for null is taken from the local program that I'm trying to fix. So similarly, if I'm inserting code, the idea that, okay, one thing I can do is insert code, that's provided ahead of time. The code that I insert in virtually all of these techniques is taken from somewhere else in the same program.
Okay, so structurally, the source of the edits can be anything, but what you're actually going to change most likely is taken from the same code base as where you're fixing the bug.
Absolutely.
Great, now I get it completely. I want to move on to another topic because fixing code, of course, is very hard, but what's also very hard is writing proper test cases. Sometimes fixing a bug involves making changes to test code, adding code to more deeply understand the bug that you're fixing. Is that something where genetic programming repair could also help to add test cases, to fix test cases?
So that's an interesting question. So the kinds of techniques I described to you, they're really assuming that the test cases are fixed. The developers provided them, and we're going to assume that they're good. And that assumption can be dangerous. A few minutes ago, we were saying, the patches, we know that at least they've been tested, so that part's done. And I was, being maybe a little bit overly optimistic there, because there are lots of times that tests are inadequate, like you're saying, and that's a risk in this kind of technique, and a reason why it's good for developers still to review the patches that are produced. But in terms of helping us find new tests, I'm pausing actually, Felienne, because there is very recent research in doing this. Well, it's funny. Okay, I'll give you a little context. So the very early work in genetic programming for program repair, there is also some work, not by us, that co-evolved tests and patches.
Yeah, that makes
but it was like the baby programs and in a subset of C, right? So and now recently people are trying to combine test generation with program repair. And in fact, that's what Facebook did. Sorry, I'm just saying these things to work them out before I say them on the recording.
Yeah, I understand. If you think it's too early or too small to really be interesting for regular developers, this is your call, really.
So that's a really interesting suggestion, Felienne. There's been some initial work in making a relationship between program repair and test generation. I don't think any of it's been, that I know of, has been really prepared for prime time or developer use. Some of it's been on smaller programs or on subsets of proper programming languages. Genetic programming and related techniques for what we call search-based software engineering have absolutely been used to help generate tests separately from program repair. So if we sort of ignore the program repair element, there is quite a bit of work in test generation and only really some initial movement towards combining the two. And certainly none that I know of that's really ready for development that uses the output of program repair to improve the test cases in an automated fashion. Now, I can definitely imagine a situation where a patch is produced against a set of tests. And although earlier we were saying, well, we have the test, so at least we know that the patch is tested, we were being a little optimistic. There are still definitely times that patches can make tests pass, but the tests weren't adequate. There weren't enough. They didn't really fully check that a feature was properly implemented, right? And so in those circumstances, I think program repair can help developers make better test suites. Because if you look at the patch and say, wow, my tests really shouldn't have let that one pass, right? I mean, it's missing this important thing. Then you can be inspired to add new test cases. I don't know of work that's doing that automatically yet, but I'm optimistic that we'll get there. Hopefully, as a research community, I think it's an interesting synergy that can really help drive program quality.
Yeah, so even though it doesn't exist, it's definitely something that could exist in the future and something that researchers are working towards a bit.
Yeah, and I do want to be clear that the connection between generating tests and even generating tests using search techniques like genetic programming and program repair, that has been explored and is actually in use at Facebook right now. So they have a technique that will automatically test Android applications and find crashes. And it feeds into an automatic program repair technique to fix those crashes. So I think that connection is already definitely being explored in practice. What we're missing is a connection back, right? So if a program repair technique finds a bad patch or realizes we need more tests in some way, to the best of my knowledge, or they're not talking about it, there's no feedback loop yet. And it's that feedback loop that I hear in your question that I think sounds interesting.
What can we do to make sure that automatic program repair works on our code base? So, of course, you've already mentioned you definitely need good test coverage, because if you don't have enough tests, then program repair is not going to find any useful patches. Are there other things we can do to, let's say, prepare the code base to be as suitable as possible to use program repair?
There are definitely things that we can do. In particular, it's not just the existence of tests that's important, but the automation of tests. So program repair techniques that assume tests really need to be able to run those tests automatically and without human assistance. If you think about the genetic programming technique, what we're doing is generating a population of 100 patches. We need to test all of them. So really a code base that is using continuous integration or something similar for regression testing, that's using automated testing, that's probably the number one thing that is the most important. Automated build as well. Generally, actually, these days, I think anything that helps you safely test or containerize your code is important, because if you think about what we're doing, we're basically, even with semantic search, we're making kind of random changes to your code and then running it. And so being able to do that safely by carefully constraining the code, maybe running it in Docker, running it in some kind of containerized solution, that makes it a lot easier to do that and set everything up in a safe test harness so you're not going to be breaking everything. So actually a lot of modern development practices, as we move towards CI and to increase containerization and even microservices and deployments like that, are automatically moving those systems to a context where program repair is applicable. Because what we really need is the ability to automatically modify, build, and test a program quickly and efficiently and safely. And a lot of build, not everybody does this, obviously, but a lot of modern build context is kind of set up to support that.
And what about specification? I can imagine, especially for the semantic approaches, if you have invariants in your code, they would very much help semantic approaches to decide, if you enter the method, it should be 2, and then if you exit the method, it should be 4. So what should happen in between is this and that. Is specification very important, or can those type of informations also be gathered from tests and test executions?
Oh, invariants would be wonderful. If developers are going to start adding those kinds of assertions, actually good assertions in test cases are really useful because they're a very similar thing. Right now, semantic techniques and heuristic techniques just try and infer that kind of information from test case behavior, but any kind of additional annotation like that would be really helpful to constraining what the program is supposed to do and figuring it out. Because it's really, a test is a fairly blunt instrument, right? And so being able to infer what X should be on line 5 from a test, that's a difficult problem and we can't always succeed automatically. So any kind of additional annotation like that developers can provide is useful to basically any kind of program repair technique. It's just another way to know what the program should be doing and whether it's doing the right thing. And those are the two real problems, right? We're trying to figure out what it should be doing and whether this change helps. Any kind of finer grained information, assertions, invariants, static checkers, anything like that is helpful.
Well, if we get bug fixes for free, then maybe that could get developers to write assertions. I don't know, maybe. It sounds interesting.
That would be great. I do think, we're seeing an increasing use of other kinds of quality checks in development practice. So people are using more static checkers and linters automatically at commit time to help check code quality. And some of these tools can find really semantically meaningful bugs, resource leaks and the like. Any kind of increased use of those kinds of tools are also helpful because they provide an extra quality check for changes that are made by automated techniques. There's even research in helping those kinds of checkers if they say, hey, it looks like there might be a bug on line 5 to suggest a change to fix it. But so really any kind of additional quality check that a developer can bake into their code base is helpful for automatic transformation techniques like program repair.
And what else? I was thinking about issue trackers. If you have an issue tracker and you have pull requests commits that say, hey, this commit actually fixes that issue, do you take that into account? So did you know this is a good edit so that we can maybe use that in the in the patch generation? Is that being used at all?
So that's not being used directly that I know of. There may be work that does this in patch generation. Although it's really useful when developers do that for researchers, because when we're trying to study our techniques, say I come up with a new program repair technique. One way I evaluate it is by trying to fix some bugs. So I need some bugs. And a common way to try and find some bugs is to go to open source projects and look for places where people fixed bugs. And so one place we look is in commit messages that connect to issue trackers. So the more developers do that, actually, the easier it is for us to see what kind of problems they're fixing and help us evaluate new techniques to help them fix it. So even though I don't know of techniques that directly use that link to try and construct new patches, we use them in program repair research all the time. So the more developers can do that, the more they're helping researchers actually come up with new and better techniques that we can then evaluate and show are useful to you.
So it's not directly useful for program repair on their own code base, but in the long run, it will be useful because it will help people like you research this and understand what type of edits are needed and improve those algorithms, right?
Yes, exactly. I don't want to preclude the possibility that new techniques in the future, or even techniques being developed right now, will make use of those links directly. I think that's a really interesting idea for research. But broadly, the practice is really helpful to people like me who do research on these kinds of systems.
Got it. So you already mentioned it briefly in the answer to one of the previous questions. These techniques already exist here and there, right? You said that, some IDEs, you can right click, hey, it seems like there's a bug here, and they already suggest fixes, and this is done with automated program repair. Is that correct? Is that what you were saying?
So there are different kinds of ways you might see patch suggestion. The mechanism that you're suggesting in an IDE, it says, oh, hey, there's a possible bug here. Here's a quick fix. That's using a different kind of technique than what we've been talking about. So we've been talking about generating patches with respect to tests. Your IDE isn't doing that, but it's still doing a conceptually similar thing, which is finding evidence of a bug and then trying to fix it. The kinds of things you see in most modern IDEs are not doing, especially complicated reasoning, but there's a lot of research that's happening right now to try and make those fixes semantically richer, more meaningful, more likely to be useful. A lot of the times those kinds of checks will say things like, according to our style guide, this variable should be declared as final. And the suggestion will be, okay, well, I'll just automatically insert the final keyword for you. That's not, it's useful, but it's not really a very meaningful bug or bug fix in the same sense that we're talking about for the last 45 minutes. But there is additional research that's working on making meaningful bug fixes with respect to those kinds of warnings that you get statically without running the program. Other work that does actually respond directly to test cases, we're beginning to see the initial deployments in industry settings that we know of. Sort of most pertinently, Facebook has recently published a couple of papers and blog posts describing their use of test-driven program repair in their actual continuous deployment pipeline, which I think is really exciting.
And are there already any tools that developers could download or try if they want to give it a go? Just say, hey, I have a bug. Let's try these automatic program repair tools and see where they're at, if they can do anything. Is this the place where we are already, or is it too early for that?
We're somewhere in the middle. There are a number of research prototypes that are available that can be downloaded. They're really not intended, as far as I know, for deployment, but an enterprising engineer with the right setup for their code base might be able to get them to work and see what happens. And I think we'd be very interested in hearing about that. For static quick fix checking, I think a lot of those you see are a little bit more ready for prime time in terms of downloading and use. As far as I know, I don't think that Facebook or other industry people who are exploring this, I don't know of anybody who has open sourced their toolchain that would allow for more immediate use for a developer. So really, it's somewhere in the middle. We have a lot of research prototypes that are at more or less readiness for use. And then we know of mature deployments, but I don't know if any of that code is accessible. So the answer is in the middle somewhere.
And are there any tools, any research prototypes that we could link to in the show notes so that if people, as you said, with the right engineering mindset, if they are interested, they could try it out?
Yeah, I'm happy to provide some of those.
Cool. This is a question I ask on almost all of my shows. So people that listen to my shows often, they might be waiting for this. What about programming languages? Which programming language is more suitable for this approach? Can we say something like this? Is there a difference between programming language in the suitability for program repair, or doesn't it matter?
That's such a great question because it's actually a pretty open research question from my perspective about which languages are better than others for program repair. All of my initial work was done for techniques for C. And C is an interesting language to fix bugs in because the compiler is very permissive. It'll let you do all kinds of things. So if you're randomly making changes to C, you can run a lot of things. They won't necessarily fix the bug, but you can certainly try many things. So in some sense, it's easy to try and repair C programs. Many different edits are possible. You can try them. But on the other hand, it's hard because the compiler isn't doing much work for you. So if a language like Java has a lot more rules about what's not allowed, and it can stop heuristic techniques from doing stupid things like inserting code after a throw statement, for example. You shouldn't do that. It's silly. It's not going to fix the bug, and the Java compiler will stop you. So on the one hand, there are fewer things you can try to fix a bug, but the things you try are more likely to succeed. So there's this tension here, and I don't know how far it goes. I don't know if very strongly typed languages end up being easier or harder. Maybe it's just too restrictive. I'm not sure. We end up kind of locked into languages a little bit by tooling, actually, because we basically need to be able to process the code. We need to be able to make changes to the code. We need to be able to compile it. And sort of once you've made that set of decisions at the beginning of a research project, you end up kind of stuck in the language. So a lot of techniques target either C or Java because of that, because of kind of the tooling lock-in, but not necessarily because the techniques themselves are intrinsically tied to a language. So to answer the question, I think some languages are probably easier to fix than others. Having a compiler with opinions is probably useful. The research community tends to kind of pick a language and stick with it for a bit to avoid having to redo everything from scratch. Although I've seen some promising work, actually one of my graduate students as well as some others out of MIT, on trying to relax some of that so we can try things on multiple languages more easily. So I'm hoping as the research community moves forward, we'll be able to answer this question more directly by trying things on different languages and getting a better understanding of which languages are more suitable for these techniques than others.
Yeah, because I can imagine, especially for the semantic approaches, if you want to try to understand what could I do here, if you have a statically typed language, you get more information on the type of a variable. So hey, this should be this. Whereas if everything is dynamic and everything's at runtime, it might be a bit harder to deduce invariants and assertions. Is that true? Or are you saying, it doesn't really matter?
I think it's just different challenges because actually the original semantic techniques were on C. And I mean, C is technically statically typed, but it's not, the type system is not helping you very much. So I think the more information does make things better. But that doesn't mean that we can only work on strongly typed languages. And for the most part, actually, the work that I know of doesn't. I mean, so Java is typed, right? But, I think we're really kind of operating between the C and the Java space for the most part in evaluating our prototypes. And more information is helpful, but it's not a deal breaker by any means.
Yeah, so does that mean you don't really take type information into account that much in generating the patches?
That depends on the technique. So heuristic techniques, it depends a bit on which templates they're using. So, it doesn't make sense to try and null check something it's impossible for it to be null, for example. So there is a little bit of type reasoning that's happening there. There has been some work in the semantic approach that says, okay, trying to limit the kind of code that can be synthesized a little bit. It's a very open space. If I say, hey, X should be 4 after this line, there's lots of code that could make X 4. So in trying to help the synthesizer, we try and give it other hints, right? And so some of those hints can come in the form of type constraints or other kinds of constraints we learn from the code just by looking at it. So having more typing information can, depending on the technique, be helpful in constraining the kinds of patches that are tried. But I don't want to speak broadly about every kind of technique because there are a bunch of different ways that this can be done. Some of them use it, some of them don't.
Yeah, so your answer is it depends.
Yes.
Right?
Exactly.
What about domains? You already mentioned that Facebook applies similar techniques to Android, and I can imagine making code for mobile is different from web development, different from backend. Are there any types of code bases, irrespective of the programming language used, for which this technique is more suitable?
I think some types of code are easier to test automatically than others, kind of incidentally. And so any code that is testable, either at the unit and also at the system level in an automated fashion. So front-end development that involves a lot of GUI testing is probably harder usually than something in the middle that can be where testing can be scripted and automated in a very simple way. I say that having just said that, Facebook is doing testing of Android applications as part of their program repair work. But that's because they have a great test harness to automatically test Android apps, right? So if you have one of those for your GUI, then it would work just fine. It's really dictated more by sort of the quality of the tool chain with respect to build and test than it is the actual, I think, program domain.
Are there any other types of programs in the broadest sense imaginable that this technique would work best on? Any ways of programming such that it would be more suitable? For example, if you use reactive programming, is that better or worse, or it makes no difference?
I think the short answer is that we don't know. I think that that's a question that researchers, we're trying to grapple with a little bit. What kinds of bugs are these techniques good for? Can we know ahead of time that these techniques would be well suited? And I think the type of programming is a question I don't know that we've tried to answer, but I really think we should. I like talking with you, Felienne, because it gives me ideas about questions that we really need to start exploring as a community. We'll have to acknowledge.
It seems like all of the questions I ask, oh, is this possible? But what about this? It's like, oh, we don't know. There's so much more research to be done here, which I think is good.
It's a fairly new research area if you think about it. I mean, we've only been as a community really working on it for the last 10 years or so. I mean, 10, maybe. There's some work before that. It's okay. I want to be a bit more fair. The kind of repair I've been talking about with you is fairly general. We're looking at sort of general test cases and trying to change the source code in general ways to fix them with the idea of kind of interacting with the standard development cycle. Before that work's really existed for the last 10-ish years or so. And we still have a million open questions, as you've probably noticed throughout this conversation. There is a fair bit of work before this general approach that looked at particular kinds of bugs and tried to preclude them, either by making changes to source or at runtime. So lots of cool systems for, can I make it impossible for buffer overruns to happen? Can I make control hijacking attacks impossible in a system? The real difference in the work is that we're trying to work on more general bugs that developers might encounter generally, which means questions about what kinds of bugs, what kinds of systems, what kinds of languages. For a long time, we were just like, can we do this at all? And now I think we're beginning to grapple with these questions about, when can we do this? When is it suitable? When does it work best? And so on.
Yeah, and I think it's just really interesting for our audience to understand where are we now, what techniques can already be used in practice, and where is this field going. So I have one more of those type of questions for you. Is this possible question?
Sure.
Because I wonder about polyglot code bases, which now is maybe almost all code bases. If you have a web application, you have some JavaScript and some HTML and some CSS, and maybe likely involving a bug would involve fixing all of these, or you need to evolve your Java code, but also your SQL code because there was a mistake in a query and also in the handling of the results of the query. Is co-evolution, patch generation for different types of programming languages within Codebase, is this something that these approaches can handle? Because I can imagine talking about human edits, as we were talking about before, this is a human edit. Often, if I make a change, I do make a change to multiple programming languages within one code base.
So I think that's a really interesting direction, although I think we have more immediate problems to solve first. So if you remember, you asked me a while ago now which kinds of bugs these techniques are suitable for, and I said fairly local bugs. And so I think I love the idea of polyglot repair, but I think problem one is to work on better techniques for multi-location, sort of intertwined repairs at multiple places in the source code. At that point, what we need is tooling to modify more than one language at a time, and I think there's research that's going to help us there. But I actually think problem one is more complicated bugs with changes in more than one place. And then we can start to worry about, okay, more than one place as well as more than one language.
Yeah, I got it. I want to come back to something you said all the way back in the beginning of the interview, but I wrote it down. It's like, oh, if we have time, this is what I still want to ask. Because at one point you said that sometimes as a developer, you can learn from the output of patch generation. So then you're generating the patch not necessarily to fix a bug, but also to get inspiration from, hey, this is an interesting way of solving a patch. And I was wondering, maybe you have a concrete example of a case that you have happened to you where a patch was generated and you read it, you're like, oh, wow, I would have never done it like this, but this is very smart. Could you give an example of that?
This is a really great question because this has happened to me a fair bit, and I don't know if I have a good concrete example. I'll say first, actually, I think that this use case is an important one, actually. I've discussed with people in industry, and I've had, vice presidents say to me, look, I don't even care if it's right. Can you just give us some suggestions to get us started? Which I thought was kind of a cool question. Because I was like, yeah, I can do that. That's, we can definitely start there. So I don't know if I have a good concrete code example, but one system that I spent a lot of time staring at was the PHP interpreter, because the PHP developers have actually very good discipline about filing issues and linking commits to the issues that they close and committing regression tests with those commits, which makes it, as I sort of suggested some time ago in this conversation, a really great system to study as a person who does program repair, because you can look back and really get a good sense of what bugs they're fixing, what tests test them, and what the bug fixes look like. But PHP is a really dynamic language, and so trying to understand bugs in PHP can be very difficult because they're all things like, well, if I call string.substring and the second argument is an 8-bit array of characters and the first argument is a floating point number, then it crashes. I'm like exaggerating, but like it feels to me like all of the bugs in PHP are like this. And so trying to understand what the PHP interpreter is supposed to do with all of these strange, unusual inputs is really hard. You look at the test cases and it's this PHP code, and it's just like, and it's really not until I start looking at patches and I see, okay, this patch is weird. Oh, but I see what the behavior is supposed to be. It's kind of like, it's an interesting way to explore a new system, especially a complicated system with weird semantics like the PHP interpreter, is to see what changes cause test cases to pass and fail. So I have a much better appreciation for the internals, especially of string processing in PHP, than I did before I started doing this work.
Yeah, I very much like that as a use case. And I can totally imagine that people would be our audience would be interested in not necessarily trying these tools to generate real patches, but exactly the case you were describing. Like, I have no clue where to look. Just let me see some patches, then at least I can get inspired. So I can see how that, in a sense, it's a lesser goal to achieve, because it's way harder to generate a real patch than to generate some things that might be sensible. But I can see how, even though it seems like an easier goal, it could also be a very worthwhile use case where, just as a means of inspiration, you would look at some patches. I really like your idea of using this also as a way to learn about a new system rather than really using it to fix a bug.
Yeah, I think that's an interesting, certainly, I don't want to just call it intermediate, but it's one of those things that can, an intermediate stepping stone that maybe we can make development better as we are working towards the goal of the magic, as you asked me about at the beginning. I think that research can be incremental and can be incrementally useful, right? And there's nothing wrong with that. I've actually had developers say to me, oh, can you just tell us what code we can delete? Because they have these big complicated systems that have been evolving for years, and test cases like, we don't even know. Can you just, and this is not a question about dead code, right? There's plenty of code that is not formally dead and you don't actually need. And so if developers have said to me, look, this sounds great, but honestly, can you just tell us what we can get rid of? And honestly, yes, right? If you give me a set of tests and say, what can we delete to make these tests still pass? We can answer that.
So we talked about many things, about generating patches, how there are different approaches to automatically generate patches as long as you have proper test cases in your code base. I have nothing more to ask, but I just wanted to give you the opportunity to add something you think we might have missed in this interview.
Well, I'm always interested in hearing from developers if they have ideas about how we can improve their lives or their workflow. So I really encourage your listeners to reach out. I'm on Twitter. So shout at me about, how your bug fixing workflow, what kind of problems you have in your code base, things that you think you want a researcher to think about to make your life better in the long run. I mean, I'd be really interested. I also want to say that if any developers out there are wondering about a PhD, and thinking, hey, this sounds really fun. My PhD program at Carnegie Mellon in software engineering, we're actually particularly interested in people with experience. And so again, I encourage you to check that out, because if it's something you're thinking about. we are always interested in students who are coming back from industry who can really bring their perspective to the software engineering research enterprise. It helps keep us connected to actual practice. So that's two things. I think I'd love your listeners to, if they have any problems they want us to think about, or if they're interested in tackling research themselves, I really encourage them to reach out, because we're always interested in hearing that kind of input and feedback and conversation.
So we'll make sure that a link to the Carnegie Mellon grad school program and also a link to your contact information is in the show note, that if listeners are interested, they can get in touch with you. Anything else we should link to in the show notes?
Oh, I was going to say, just shout at me over social medias. Anything else to link to in the show notes? Well, I think, there are a couple of papers, I think, that are accessible that we can link to. You mentioned a talk that I gave, and I actually think that was for a sort of half and half industrial research audience. So if people want more details, like technical details about how these techniques work, that might be a good resource. And then I think we also said, I'll just throw some links up to the Git repository for existing research prototypes for your sort of enterprising listeners who want to play with them, as well as we have a good bibliography actually online that we maintain. So if someone wants to take a deep dive on the literature, we can provide that link as well.
Great. Well, that's it from my part. Thank you so much, Clara, for being on the show.
Thanks for having me, Felienne. This has been really fun.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.